Now let's run through questions on principle of moments. So the key formula that you need to remember is to calculate moment is force multiplied by perpendicular distance to point of reference. Sometimes teachers like to say to the pivot, okay, which yes, a pivot can be a point of reference, but so it can be actually any point on the system. Let me just show you, but the important thing is that distance need to be the perpendicular distance. This is critical. So let's look at this system over here. So here you have like a cupboard latch that is held onto the wall by a hinge, so you can move this way. The weight of the board is going to pull it downwards, right? So to lift it up, there need to be maybe a string or person pushing it to keep it in place. So let's say if it's in place over here, it means that all the forces are being balanced. So it doesn't continuously turn. Let's just look at A, B, C. So if we consider A, B, C, there are three different set of moments. So the first thing we want to determine is where do you take moments about? Because where you take moments about will affect your distance. It's just like if somebody asks you the question, how far is it? That question is not complete. You must say, how far is it from this place? So that is your place of reference. So if I know this force, and I don't know this force, I can actually take moments about A. And then suddenly A disappears. So A becomes my point of reference. Then the perpendicular distance will be from the force all the way to A, C to A. So we are talking about this distance, let's call it dB, and this distance, let's call it dC. So moments, we can divide them into clockwise and counterclockwise. So where you take moments about is the center of the clock. So this is your center of the clock, so it moves this way. So 12 o'clock is here, 3, 6, 9. So this is clockwise. If this is the center of the clock for this, then it moves around here, moves around the center. So this is your counterclockwise. So clockwise moments will be FB multiplied by DB is equals to FC multiplied by DC. So since DC is much longer than DB, this force will be lesser than this in order for moments to balance. We can also take moments about point B. If we take moments about point B, then B becomes the center of the clock. Then we have to consider force FC and force A. So over here you have a hinge that's holding. So most likely there's a nail or something that's holding it up. So there is a force that's pushing up this way. So you see, so this is our moments for FC. This is our moments for A. It has to go the other way so that it will balance it out. Then FA multiplied by something is equals to FC multiplied by your distance. In this case, your distance of DC will be just to our point of reference. So this is the key, this is the center of the clock. So the distance will be from here to here. So let's call this DC1. DC1, FA multiplied by here to our point of reference again, and it is perpendicular. So this line is up, this is perpendicular. So let's call this DA. So this is balanced. Okay, later on in your questions, you are going to see questions as like this, where the forces and the plank is not perpendicular. So when you calculate, let's say if we take moments about A, or sometimes they say A is the pivot, then we know that we have to use FC. So let's say moments of C will be FC. Do you multiply it by this distance, which is, let's say the length of this whole plank is C1? Do you do this whole thing? So this distance is not perpendicular to the force. So you have to find out what is this, C2. So it has to be Fc multiplied by C2. Then you get your moments. So because the force is a vector, so you already have a direction. So you have to mark 90 degrees from the force. Similarly for your FB, so this is the center of the clock. So FB is your clockwise moments. So FB need to multiply by this distance, B2, for you to get the answer. Let's just walk through some of the questions for you to better understand this concept. Let's look at the next question from 2016 paper. So we have, this is part B of a question. So 30 bricks is 869.4 newtons. It's calculated in the previous part. So we have a wheelbarrow. Weight is 110. So I'm going to add in this information inside. Downwards here, 110 newton. Line of action of the combined weight of wheelbarrow and bricks lies at 0.8. So extend this line, this is perpendicular. So this is the distance that I want. Vertical force applied at the handle, 0.5 meters away from the line of action. As shown in figure 2.1, calculate the force needed at the handle to hold the wheelbarrow and the bricks in position. So firstly, we have to set where do we take moments about. So taking moments about, so we can take moments about pivot P, we can take moments about here, we can take moments about here. If wherever the place we take moments about, the data will disappear. So we want to find force F, so we cannot take moments about here. And we need the data over here, we cannot take moments about here, so we use the pivot. So this is our center of the clock, so we have this moment going clockwise, F is going counterclockwise. Clockwise equals to anti-clockwise moments. So clockwise first, it will be moments caused by the bricks plus moments caused by the weight of the wheelbarrow. So there are two sets, and since they are acting at the same spot, we can actually group the forces together. So we take 869.4 plus 110 multiply by the distance to the reference point, which is 0.8, is equals to anti-clockwise moments, which is F, what you want to find, multiply by. Okay, so why do they give you 3 marks? Because what distance do you use? Do you use 0.5 or do you use 0.8 or you use the whole distance? So this is the reference. So we need this whole thing, this whole distance, which is 0.5 plus 0.8, 602.7 newtons. So this is your force. So these two questions are pretty straightforward. Let's look at the more complicated ones. Okay, this question from 2015 paper, 5 marks attributed to moments. So you have bicycle, pedal. Sometimes they like to put complicated things inside, but actually it's just essentially the same. If you strip it down to just lines, it will be much easier to understand. So no need to look at the chain and all this T-jaw and all that, it doesn't matter. As it moves along, the pedal moves through a radius of 8.0 cm. So this distance is 8.0 cm. For the pedal shown in position at 6.1 in the diagram, F is 5.0, so this is perpendicular distance away from pivot. Calculate the moment of force about the pivot. So this is the reference point, we have our force, we have our perpendicular distance 90 degrees. Moments equals to 110 multiplied by 5, so it's 550 Newton cm. Pedal moves from position A to B as shown in figure 6.1. So it moves from here, this point, to this point. Explain why the force applied at A will have a different effect from the force applied at B. Let's see what is the difference. So if a force is applied over here versus it over here. So actually when the force is applied over here, when it's right at this point, okay, when you ride bicycle as you pedal, there will be some parts of the pedals that is harder to push and some parts that's easier, right? So was it harder to push when your feet is vertically like upwards on this? So actually when you are at A at this point, you can only push it forward. You can't actually compress it down because you're acting against the whole arm. So let's say you are slightly off from over here at this point, and then you are pushing it downwards over here. Then the perpendicular distance is just this short little place compared to the perpendicular distance of this force to this point. So this is much bigger than this. So this will produce a much smaller moment. That's why over here is much harder. Produce a similar turning force at the gear that will turn the wheel. So the force will have a different effect. So force applied at A will produce a smaller moment as compared to same force applied at B. So this is in a sense the conclusion, but it's 3 marks. I need to write a little bit more. This is because the perpendicular distance of force A to the pivot is much lesser compared to the perpendicular distance of force B to the pivot, which is actually 8 cm. So the effect over here is different because the distance is different, so force is the same. So this is how you tackle this question. Let's move on to one last one. Now let's look at this question from 2018. This is very interesting because the entire question is about the principle of moments. So although it's in section B, but it's 10 marks worth. Let's just quickly go through it. So we have a ram of weight 165 and the length 260 cm fixed to a lorry as shown in the whole figure. So there are actually two forces here, one vertical force upwards, one horizontal force FH. This is 100 cm, 240. Okay, calculate the clockwise moment about the NO of the ram. What is key is that, so where we take moments about, so this is our center of the clock. So let's go through these three forces that are here. So when we take moments about here, we don't need to think about forces around here. So we cover this. This is the center of the clock. This goes this way. So 165 is clockwise. FH goes this way. So it's anti-clockwise. FV goes this way. So it's anti-clockwise. So our clockwise moment is mainly produced by our 165 newtons. Let's quickly solve it. So clockwise moment will be equals to 165 multiplied by perpendicular distance to O. So what is the perpendicular distance to O? Is it 130? It's not 130 because this angle is not 90. So if we extend this line, we are looking for this length over here. How long is this? So if you extend this whole picture into a rectangle and take the ram as a diagonal, so actually this part will cut right in the middle. So this is actually half of the entire 240, so this 120 cm. So clockwise moment is 165 multiplied by 120. So your answer will be 19800 Newton cm. Part 2. Write down an expression for the anti-clockwise moment about NO of the ram. So just now we have already marked it. So we are looking at these two forces. So let's just go a little bit deeper. So what is FH? FH is actually the normal force, which is a contact force. So the lorry, there's a normal force that's pushing it back upwards. FV is actually a frictional force in a sense to kind of prevent it from sliding down. Okay, so that's why there are kind of like two forces if you need to rationalize. So we have to do moments for FH. So for FH, we ask ourselves what is the perpendicular distance. So FH pairs with 100 and FV will be the entire 240. So anti-clockwise moment will be equals to, first we have FV So FV, your perpendicular distance, is 240 plus FH, our perpendicular distance, is 100. So 240 FV plus 100 FH Newton cm. So this will be an expression. That's your 4 marks. Part B. So it says a man is standing on the ramp, begins to climb the ramp. State how the clockwise moments about point O change, if at all, as the man moves up the ramp. Explain your answer. So let's consider extreme points. Let's consider at point O and just right on top of the ramp. So this man here will exert a force downwards caused by his weight. We call this Fw. So Fw will stay consistent as he moves up. What changes will be his distance to our point 0, his perpendicular distance. So let's write down the answer. At point 0, the man does not change the clockwise moments, because over here distance is 0, so force multiplied by 0 is 0. But as he moves up the ramp, his weight will exert a clockwise moment, which is a factor of his perpendicular distance from O. The further up the ramp, the greater will be the clockwise moment added, since distance will increase. So this is how I'll write the answer. I know it's a lot mouthful, but the main thing is you're trying to tell them that as he moves up, distance will increase. Because distance will increase, we'll have more clockwise moments being generated. Okay, next. Suggest a point at which another force must act on the ramp. Okay, this part of the question is a little bit tricky because what is the context of this question? So sometimes when you see questions in subparts, like here B part 1, part 2, part 3, it's always good to continue reading the next question, because the next part will actually give you a clue of this. By considering moments about the top T of the ramp, explain why this other force is necessary. So this gives us a clue. So part 3, if they take moments about here, then this other force need to be activated. So the point at which another force must act on the ramp cannot be at point T, because if your answer is at point T, then when you consider moments about top T, this other force will also disappear. So remember, when a system is in equilibrium over here, you can take moments at about any point. So in this case, there's just point O, center of the ramp, and point T. These are our 3 choices. Okay, so the direction of moments at point C is not going to change. Okay, this is according to these 2 forces. So when we take moments about here, then point C will generate, this is now the center of the clock, point C will generate anti-clockwise moments. So in order for system to be balanced, there has to be a clockwise moment that is balancing. So the clockwise moments must come from here at point O, must be a clockwise moment that's going upwards this way, that is balanced. So actually this force is our normal force that's acting upwards. So the ground is pushing the ramp upwards so that it doesn't rotate. So the point here is point 0. And the next part, explain why this other force is necessary. When considering moments about the top T, anti-clockwise moments is produced by the weight of the ramp. Therefore, a clockwise moment and upward force need to act at point O so that the system is in equilibrium. Okay, so that's the answer. Keyword is equilibrium. upward force, which is a clockwise moment. So that will give you your 3 marks. So this part is slightly more challenging, so that's why it's worthwhile to go through.